Within an exascale enterprise environment, data flow is constant. The integrity of that flow is the primary concern for any security architecture. But despite increasingly complex security perimeters, modern threats, designed with high-level automation, often move through these enterprise environments unimpeded. To counter this, most organizations employ defense in depth. This involves layering deep packet inspection, heuristic endpoint detection, and multiple firewalls to catch what the previous layer missed. The core of this strategy is semantic logic. It is a model that must constantly decode and evaluate every piece of data to answer a single question: is this code malicious? This creates a massive computational tax. Inspecting every packet consumes CPU resources meant for enterprise workloads. Furthermore, these layers fail against encrypted channels. Since scanners cannot read the payload, the threat remains invisible, no matter how many inspection layers exist. This creates a defensive model where millions are spent on hardware and software unable to process the very threats it was designed to find. To stop threats that hide within encryption, we have to look past the code itself and focus on how data behaves within the network structure. This is the operational philosophy of the PTCP Omnibus Cage, payload-blind containment. Instead of software inspection, this approach treats the network as physical geometry. Every data flow is measured by its physical footprint on the network topology. To manage this, the Omnibus Cage uses a tensor train model. This mathematical framework compresses the network's complex physical geometry into a lightweight, high-performance map. This replaces the power-hungry DPI arrays. Instead of scanning code, the system simply verifies that the data flow follows the established physical laws of the network architecture. An attacker can encrypt their code or use zero-day exploits to remain undetected by scanners, but they cannot hide the physical footprint of their movement across the network. By monitoring the physical mesh, the system identifies anomalies in real time across a massive enterprise footprint. We can see how this works against specific tactics, such as lateral movement and network pivoting. If an adversary attempts to move from a compromised workstation to a secure database, they must alter the geometric curvature of the network fabric, triggering an immediate detection. It also accounts for slow drip attacks, where an adversary tries to avoid detection by gradually changing baseline traffic patterns over time. The system prevents this through dual-horizon genesis anchoring. It compares current, active traffic against an immutable baseline recorded at the time of deployment. This prevents an attacker from slowly subverting the model. Any deviation, no matter how gradual, is constantly measured against that original mathematical anchor point. But what if an attacker avoids the network entirely? A localized ransomware attack might detonate on a single host without ever attempting to move laterally. The final containment layer is the semantic topological bridge, which connects the network mesh directly to the physical hardware of each host. Even the most advanced malware requires massive physical effort to rapidly encrypt a local hard drive. The bridge continuously monitors for this physical hardware exhaustion, tracking the massive disk I/O spikes that occur during unauthorized encryption. Because this relies on physical measurement rather than code signatures, even a localized zero-day attack is stopped by the friction of its own execution. Detection is only effective if the response happens faster than the attack. Human reaction times are too slow to prevent modern data exfiltration. To solve this, the Omnibus Cage uses an automated geometric kill switch. When a violation is confirmed, the system responds in milliseconds, autonomously severing the compromised node at the hardware level. This containment happens via the network switches or local firewalls, before the adversary has time to move or steal data. This hardware-level security model directly impacts enterprise budgets. By consolidating redundant semantic tools into a single model, organizations reclaim massive CPU overhead lost to legacy arrays. This leads to higher ROI, as automated response prevents the downtime and forensic costs of a successful breach. By moving from code inspection to physical measurement, the PTCP Omnibus Cage allows enterprises to unify their defense behind a single perimeter defined by the network's own geometry.